All right, this week's lesson is on piecewise functions. So today we're going to look at piecewise functions in general, and then in the next lesson, how to find the limits of piecewise functions. So as an example, a piecewise function is something that's one part of the graph is one function and another part of the graph is a different function. And it can be two different things, it can be three, it can be really an unlimited number. So let's just take an example like this where we kind of split the graph into two parts, where x is greater than 1 and where x is less than 1. So in a piecewise function, we're going to have two different domains. We're going to have when x is greater than 1, and we're going to have when x is less than 1, or less than or equal to 1. Again, this is just an example, so it doesn't always have to be just two parts of the graph, and it doesn't have to be split up at 1, but this example is. So let's say that when x is less than 1, the graph is just the quadratic x squared. And when x is more than 1, the graph is, let's say, 2x plus 3. So how to graph this? Well, you can do this a couple of different ways. You can either graph the entire part of the function, for example, x squared. I know that x squared is a parabola that opens up like that. But we only want this graph when x is less than or equal to 1. So when x is less than or equal to 1, we're looking at this part of the graph. So what I can do is I can kind of erase the part of the graph that is not less than or equal to 1. And then same thing happens when we are looking at when x is greater than 1. We're looking at this function 2x plus 3. So again, if you wanted to graph that entire thing, that has a y-intercept of 3 and a slope of 2. So up 2 over 1. But then again, you're going to want to get rid of the parts that are less than that. So again, let me draw the rest of the graph in there. So as you can see, I'm going to change that to be a open circle. So on one side of 1, on the left side of 1, we have the parabola. On the right side of 1, we have the linear function because it's split up. And that's how you would draw a piecewise function. A couple things to note. Whenever we have less than or equal to, that gets a solid dot. Whenever we have just strictly greater than, that's when we have the open circle, because we're not including that point. We're not including 1 in that linear function. A second way to graph this would be to just kind of look at where it connects to the line, and that's the way that I typically do it. So what I would do when I'm graphing this is I would look at this parabola and I would say at 1, because again that's where it connects, where does this graph equal? So I'm going to plug a 1 into this equation and I get 1 squared is 1. So I know that this function crosses at 1, and from there I can draw the rest of the parabola knowing what it looks like. Same thing with the linear function. When I plug a 1 into the linear function, I get 2 times 1 plus 3, which is 5. So 1, 2, 3, 4, 5. So I know it crosses at 5, and then I can draw the rest of the linear function. To me, that's an easier way to do it, just because you can tell where it crosses. And when it comes to limits, which we'll get to tomorrow, you can see why that would make sense, why we would want to know where it crosses. So as x approaches 1 from the left, I know that that's 1, and when it approaches from the right, I know that that's 5. But we'll get to that tomorrow. All right, so let's look at some examples of how to graph exponential functions. Not exponential, piecewise. So I always draw in my break line. In this case, it's at -2. Again, sometimes there's more than 1, but in this case, there's just the 1. So I'm going to plug in a -2 into this function, and when I do, I get +3. And because it's just less than 2, I'm going to put an open circle at 3. And it has a positive slope of 1, which would look like that. All right, I'm going to do the same thing here. I'm going to plug in a -2 there. And when I plug in a -2, I get 4 minus 4 plus 3, which is 3. So that also crosses at 3. And then the rest of the graph, I can try to figure out. When I plug in a 0, I get 3, so it looks like it should be something like this. And again, you can verify that using Desmos or something like that. So is this a function? Yes, it's a function. Let me back up. Because this was greater than or equal to, that's why I closed in that circle. So when you close in an open circle, it's as if that point is just there. So what is f of 3? Well, that would be the pink function because it's more than -2. So when I plug in a 3 here, I get 9 plus 6 plus 3, which is 18. When I plug in a -4, that would be the blue function because it's less than -2. -4 plus 5 is 1. And when I try to plug in a -2, that would be the pink function because it is equal to -2. And that would be where it equals 3. All right, let's take a look at example 2. We'll do the same thing. Again, this one breaks at 2. So I'll draw a blue function and a pink function. So the blue function, I'm going to plug in a 2. And when I do, I get -4 plus 1, which is -3. And that's going to be a closed circle because it's less than or equal to. That is a slope of -2, which looks like that. All right, for the pink function, I plug in a 2, I get 6. 2, 3, 4. That's an open circle, and that has a slope of 5, which is going to go off the page pretty quickly. So is that a function? Yes, it's a function. When I plug in a -4, that will be the blue function, and I get -7. When I plug in an 8, 8 is greater than 2, so that's the pink function. That would be 36. And when I plug in a 2, that's the blue function because it's equal to 2, so I get -3. All right, pause the video at this point. Try the next couple examples, and then check your work. All right, I'll assume that you've done that. Here is how example 3 looks. I did not go through this, but this is a function. When I plug in a -2, that's going to be the pink function, which would be 3. When I plug in a 0, that would also be the pink function. That would be a -1. And when I plug in a 5, that would be the green function, which would be 9. All right. So the next type of problem is working in the opposite direction, taking a piecewise graph and coming up with a function. So in this case, we're going to have 2 separate functions. I'll draw them in. There's the pink function, and there's the blue function. The blue function exists. Here's the deal, that this is either blue or pink. It's the same dot, so it doesn't matter which one you give the function to. You just can't give it to both. So we'll give that to the blue function in this case. So the blue function exists when x is less than or equal to 0. And the pink function exists when x is greater than 0. And like I said, this equal sign could have gone to the pink function because it's the same point. Okay, so let's draw these functions. Let's see what the equations are. Well, the pink function has a slope of 2 and a y-intercept of 0, so that would be the linear equation y equals 2x. The blue function has a slope of 1 and a y-intercept of 0. So that's a pretty straightforward example of how to find the linear or the piecewise functions that go along with that. All right, let's try example 5. Example 5, we have two parts here. We have this pink part right here, and then we have this blue part that goes right there. And again, the points match up, so it does not matter which one we give it to. So we have two functions. All right, let's go blue on top, pink there. So the blue function is when x is between -1 and 3. And the pink function is when x is between -3 and -1. And let's take a look. The blue function is a slope of, let's see, down 3 over 2, so -3/2. And it looks like it crosses at 2.5. So that shouldn't have been too bad. The pink function is a quadratic, so the best way to do that is to see which way it's been shifted. And this one's been shifted to the left 3, so that would be an x plus 3 squared. And then it has not been shifted up or down, so there is no plus on the outside. All right, pause your video here. Go ahead and try example 6. All right, in example 6, we have two linear functions that are broken up at -2. And then we have a -x plus 5 and a -2 function. All right, finally, an application problem in example 7.